A fractional expression is a fraction which has an algebraic expression as its numerator and denominator. Now, a rational expression is a fraction in which the numerator and denominator are polynomials. It's a subtle difference, but at any rate, rational expression, the quotient of two polynomials. That means a fraction in which the numerator and denominator are both polynomials. All right, let's talk about rational expressions here for a bit. First of all, we're going to talk about reducing them. And to reduce them, we end up factoring and canceling like factors. Now, this is really a duplication of our method of reducing regular numerical fractions that we are familiar with. 2/6, you see, reduces to 1/3 because we're taking out a common factor in the numerator and denominator. Same idea here. We take the numerator, a trinomial, factor it. Take the denominator, factor it. You see, we're taking a common factor out of the denominator and we're factoring the numerator by using the general method. Now notice that the x minus 2 factors are the same. So we can eliminate them. Those cancel. And we have x plus 6 over 3. Now, two things to note here at this point. First of all, we cannot cancel the 3 with the 6. All right? We can only cancel like factors. And this 6 is not a factor of the entire numerator. It's an individual piece of a binomial. You see, the 3 factor in 6 is a piece of a binomial. So it's not a candidate for cancellation. The other thing to notice is that I've written here x is not equal to 2. Now, look back at the beginning. I factored 3x minus 6 into 3 times x minus 2. But you know, we have said that denominators cannot take on the value 0. So it means that x cannot take on the value 2 here, because 2 minus 2 would be 0, 3 times 0 would be 0, this denominator would be 0, and we disallow that. Since this expression and this one are equivalent to one another, we lose track of the idea that 2 cannot appear here in this denominator. And so we write x is not equal to 2. Let's dwell on that just a moment. This is, we're designating what's called a domain here for our expression. The domain, back over here, the domain is roughly the acceptable replacements for variables in expressions. In this expression, in 3x squared minus 5x plus 2, the acceptable replacements for x would be all the real numbers. If we replace x with any real numbers, this makes sense. Now, what about for this, the square root of x minus 2? Well, you see, x is restricted in its replacement. We can't replace x with, for example, 0, because we would have the square root of 0 minus 2. The square root of a negative number is not a real number. So our domain here would be x's, the ones that make sense, would be x's that are greater than or equal to 2. Numbers that are larger than or equal to 2 for x would cause the radicand here to be either 0 or positive. For this one, for this little fractional or rational expression, x cannot take on the value 3. So we would write as the domain all real numbers except 3. Now, instead of saying all real numbers except 3, we understand we're talking all real numbers, and we just list the exception. X cannot be equal to 3. That's a way of writing the domain. Now, in a problem like this, when just looking at a fraction like this, it isn't necessary to write down the domain because it's sort of implied by the existence of the problem. The problem is here. We see that the denominator involves this binomial. We understand that x cannot take on a value that would cause the denominator to be 0. We agree upon that. So we don't have to write this down every time. But if that denominator somehow disappears from the problem, as in this problem, you see, if this factor disappears from our problem by reduction, then we have to say, gee, we've lost something in this problem. In our original problem, x was restricted from being 2. And we have an equivalent form here in which it isn't evident that x can't be 2, so we have to write down x can't be 2. All right, enough of that. Let's reduce this one. All right, the whole idea in reducing fractions is rational expressions, this kind of fraction, is to factor both numerator and denominator and eliminate like factors. So in the numerator, we would factor into x plus 10 times x minus 2. In the denominator, we have x plus 10 times x plus 1. And we can cancel then the x plus 10s. Now, what we get is what's left over in the numerator and denominator. X plus 2 for the numerator, x minus 2 in the numerator, x plus 1 in the denominator. And we have to say what our domain is here because we lost a part of it. We lost a particle of it up here. We eliminated the x plus 10 factor in the denominator, so we have to say that x cannot be equal to negative 10. X cannot be equal to negative 10 in this expression because it was disallowed in the original one because it's a value that causes the denominator to be 0. Right. Here's a little nuance that occurs in reducing algebraic fractions or rational expressions. 3 minus x over this trinomial. Factor the trinomial and we get x minus 3 times x minus 2. Now, what we notice here is that 3 minus x and x minus 3 look an awful lot alike. In fact, to see exactly how they differ, let's take this numerator and swap the terms around. Let's write the x term first by just writing the negative x first and then plus 3. Now we can see very clearly that the binomial in the numerator simply differs from this factor by the change in the signs. So if we can somehow perform an operation that would change these signs, then we will have a cancellation possibility. Now, of course, we are not allowed to multiply through here by negative 1. That would change the signs, you see. Because if we multiplied by negative 1, we would change the value of the entire expression. We don't want to do that. We just want to change its form, not its value. So what we'll do is, instead of multiplying through by negative 1, we'll factor out negative 1. And it accomplishes the same thing. When we snag out a negative understood 1, and I'll write the 1 here just for emphasis, but we pull out a negative 1 factor from this term. You see, negative 1 times x is negative x. So we pull out negative 1 and we have x. We pull out negative 1 from here. Gee, there's no negative 1 there. Well, we can think of it as negative 1 times negative 3, you see. So when we pull that negative 1 out, we're left with the negative 3. Now, the short way to think about it is like this. When you pull out a negative sign or negative 1, it simply serves to change all of the signs in the polynomial over which you're factoring. So we pull out the negative 1, that sign changes, this sign changes, and we go on about our business. All right, now we have the x minus 3's going out, and the negative 1 is left in the numerator. Often now, this 1 wouldn't be written here. It would be just a minus sign at this point. But once the cancellation is done and once we write our answer down, we plant the 1 in there to emphasize that that is the number that's left. We can't just put a minus sign by itself, you see. All right, so our answer then can be written like this, as the negative 1 over x minus 2. And again, we write our domain. We canceled the x minus 3, so we know that x cannot be equal to 3 in this expression. Another way to write this answer is to allow this sign of the numerator to float as the sign of the fraction itself. Now, these are equivalent to one another. Neither is sort of better than the other, but certain circumstances would dictate that one or the other might be used. Multiplying and dividing rational expressions follow nicely our idea of multiplication and division of regular fractions. We follow a similar kind of procedure. Here, in multiplying these rational expressions, what we do is we factor every numerator and denominator and eliminate like factors. And this cancellation process of factors in numerators and denominators is fine for any numerator, a factor in any numerator with a factor in any denominator, which implies that we can cancel up and down, or we can cancel diagonally in either direction. Right here, we've factored all over the place, and I've got an x plus 2 factor here and an x plus 2 factor here, so they can eliminate one another. This x plus 1 has no partner up here, or no like factor to cancel with. The x plus 1 and the x plus 1 here don't cancel because they're both in denominators. Now, this x can cancel with one of these x factors, which leaves an x factor here. Now, once the smoke clears, we simply identify all the leftover factors. For all the numerators, we have x minus 1 remaining. In the denominators, we have, let's see, we have an x factor here, an x plus 1, and another x plus 1. So we have x and 2 factors of x plus 1. Now we notice that what we have eliminated here, we've eliminated x plus 2, which tells us that we have to identify that x cannot be equal to negative 2 in this particular problem, because the implied domain is no longer there. Now, we eliminated one of these x factors. If we had eliminated both of them, we would have to say x cannot be 0. But we are left with an x factor here, so we don't have to do that. The x can't be 0 part is implied by the existence of this x factor in this denominator. Division of rational expressions follows a similar format. That is, we factor everything in sight, and we look for cancellation possibilities. The only difference is that to divide, we end up changing our problem from a division problem to a multiplication problem, just as we do with regular fractions. We say that we multiply by the reciprocal. Effectively, what we do is just flip the second fraction over. Well then, we have two things to do here, don't we? We have to flip this fraction over, and we have to factor numerator and denominator. Now, at first, it may be a little dangerous to do both of those things in one step, that is, factor and flip over. Eventually, though, you'll get comfortable with that idea. Here, factoring this numerator, we get x plus 3 times x plus 2. We bring down x minus 4. This numerator becomes the denominator here because we're flipping over, and this becomes x plus 3 times x minus 2. This denominator becomes the numerator, and we take out the common factor, 5. All right, now it's a multiplication problem, and we follow the same kind of procedure that we did earlier. All right, we're looking for like factors to cancel. The x plus 3's can go out here. Let's see, x plus 2, x minus 2. No, we can't do that. Now, you know, we can't, we had a way of changing signs earlier in numerator and denominator by factoring out negative 1. Now, that's not a possibility here, because when we factor the negative 1, it would change the signs of both of these terms and not just the sign of one of the terms. So that procedure won't work here. All right, so we only have one sign difference. The 2's, you see, are different in sign and not both of the terms. All right, let's see. We've got the x minus 4's going out here, and I look around for other cancellation possibilities. I don't see any. I'll just bring down the leftover factors. We have 5 and x plus 2, so 5 times x plus 2 in the numerator. In the denominators, I've got simply x minus 2. Now, I've eliminated a couple of factors here and here. That allows me to identify the domain, you see. We know that x cannot be equal to 4 because of this cancellation. X cannot be equal to negative 3 because of this one. Notice I've left the problem in factored form here. Sometimes your teacher will require that you expand this, write it in the multiplied out form, and sometimes it's okay to leave it in factored form. A lot of times that depends upon what use you will make of the problem later. Well, let's add and subtract algebraic fractions. The adding and subtracting was saved as last, or after the multiplication and division, because the process is somewhat more lengthy. Now, again, though, we're going to follow the same process that we did in adding and subtracting regular fractions long time ago. We need a common denominator. Here's a problem in which we have that common denominator. We have 3x minus 1 over this denominator, 4 minus x over the same denominator. When there's a common denominator, you know, all we do is collect numerators. It's kind of like this. You know, back some time ago, you might have seen a problem like 1/5 plus 2/5. And we say we have 3/5, or an intermediate step might be like this. We simply add the numerators and retain that common denominator to get the 3/5. Well, we're going to put that intermediate step in this problem. What we would do is we identify that we have common denominators, so we say, all right, let's collect the numerator. So we write 3x minus 1 plus 4 minus x. You see, just bring down this numerator, and over the common denominator. Now, if this were a subtraction problem, and we had the common denominators, we would be subtracting this numerator. Now, that's a little bit tricky, and we'll talk about that in a little bit, but we would be subtracting the entire numerator here. All right, so collecting up in this numerator, 3x with the negative x gives us 2x, and negative 1 with 4 is 3, and in the denominator, x plus 3. Now, we cannot cancel these 3's because these are individual pieces of binomials and they're not factors. We can cancel only factors, you see, involved in fractions. Here's another one. This one, in this one, we don't have the common denominator situation. So what we have to do is go through a factoring process. In causing the condition of the common denominator, what we do is we factor the denominators involved. And we're looking to cause the factors to look alike in both denominators to make that common denominator situation. Here's what I'm talking about. Here we have 3x minus 12 factors to 3 times x minus 4. Now 5 is already in a factored form. Now, in identifying a common denominator, we identify the common denominator by saying the common denominator contains every different factor that we see. All right, so the common denominator will need to involve 3. The common denominator will need to involve x minus 4. The common denominator will need to involve 5. See, every different factor that we see. Now, 5 becomes, I'll write it as a factor here. So the common denominator is really 15 times x minus 4. And it's important to write that down somewhere because we're going to need to refer to it from time to time. All right, now, to cause these fractions to change their form, not their value, change their form to become new fractions that have that common denominator, we simply ask ourselves what factor or factors would be missing from each of these denominators. All right, from this one, you see, 3 times x minus 4. What factor is it missing to make it look like this or that? It's missing the 5 factor. So what we do, whether we just think about it or whether we actually write this down, is this. We're going to multiply here by 5 over 5. Looks like I've painted myself in a little corner here, doesn't it? At any rate, we're multiplying by 5 over 5 in both, we're multiplying by 5 in both numerator and denominator. In multiplying by 5 over 5, we're multiplying by a form of 1, which doesn't change the value of the fraction. Multiplying by 1 doesn't change the value, but it does indeed change the form, and that's what's important here. So 5 times 5 in the numerator becomes 25. We'll go ahead and expand that. Here we have the common denominator, 15 times x minus 4, and we leave the denominators in factored form. Now, here, let's see, we have 3/5. So we look over at our common denominator and we say, what factors are we missing? Because we're going to take this this fraction and multiply, just jam those factors into this denominator. And in doing so, we need to multiply those factors into the numerator as well. Well, we need to multiply certainly by 3, so we'll multiply by 3 over 3. We also need to multiply in the x minus 4 factor, so we'll multiply that factor into both the numerator and denominator. Now, all the activity here is in the numerator because we know our product here. We've set it up to give us the common denominator, so we can just write that common denominator down. Now, in the numerator, 3 times 3, 9. 9 times x minus 4 is 9x minus 36. All right, we have the common denominator condition. Now we collect numerators. We're going to take this numerator and add that numerator. And now we've strung out our terms. We collect the like terms. That means collect these constants to get negative 11. So we have 9x minus 11, and in the denominator, 15 times x minus 4. Now notice again, the denominator was left in factored form, and it's left in factored form throughout our problem, whereas the numerators were expanded. Why is that? Well, it's because we need to expand numerators because it turns out that part of this process is to collect the various terms that are involved in the numerators. And if they were in factored form and not expanded, you see, we couldn't do that. So we have to expand or multiply out numerators in order to collect the various parts. In the denominator, however, we leave it in factored form because at the end of the problem, there may be a possibility of a cancellation. we could occasionally factor the numerator in such a way that we'll see like factors. And in order for us to be able to do that, the denominator needs to be left in factored form. This problem involves subtraction. Now, we approach the problem the same way. We're looking for a common denominator. Our first step in that process is to factor both of the or all of the denominators involved. Here, there are only two, so we look for a factorization. Well, I don't see one. These are already so-called primes. So we'll identify a common denominator as being every different factor that we see. Well, x minus 3 appears here, so x minus 3 is part of our common denominator. And 3x plus 4 appears here, so 3x plus 4 must appear in our common denominator. So here is our common denominator. Now, in order for us to change these fractions into new ones that have that common denominator, we'll need to multiply in the missing factors, the factors in the common denominator that are missing in each of these denominators. All right, this denominator is missing the 3x plus 4, so we'll multiply here by 3x plus 4 over 3x plus 4. Now, it may be helpful for us to tack on or write this denominator in parentheses here. Now, what we'll do in our next step, to go to our next step, we'll simply do the multiplication implied in the numerator. X times 3x, 3x squared, x times 4, 4x. For this one, we're going to multiply into the denominator x minus 3, the missing factor, the factor that's needed to complete that common denominator. So what we'll do is show this, the 3x plus 4 in this denominator, and we're multiplying by x minus 3 in the denominator, and we'll do the same thing in the numerator. In the numerator, 2 times x minus 3, 2x minus 6. Now, here's a common error. Be careful about this situation in subtracting fractions. What we intend to do here is subtract this numerator. And the mistake that's often made is that the 2x minus 6 is brought down, the minus sign is put between, and we would have minus 2x minus 6. Well, that's not exactly true, because we want to subtract all of this. And thinking about it in a parenthesis helps us understand what needs to happen. The negative sign precedes the parenthesis, so all of the signs within the parenthesis must change. So this becomes minus 2x plus 6. All right, now let's collect the like terms. We have 3x squared, 4x minus 2x is 2x, and we bring down the 6. And this becomes our final answer. Notice that I would be looking for a possible factorization here that would lead to a cancellation. I don't see any, so this is my final answer. Well, let's look at another one that's even a little bit more imposing, perhaps. This one involves 3 fractions. Now, again, the first part of the process is for us to identify a common denominator. To do that, we look at factors. So, factoring here, well, it's already factored. Factor here, it's already factored. X squared minus 1, difference of squares. So we factor into x plus 1 times x minus 1. Now we have listed all of our factors. And by the way, just for a moment, let us understand a little concept here about as the problems grow more and more complicated, how do we deal with that? Well, there are a couple of things, but fundamentally what we do is we become more organized. You deal with greater complication by improving your organizational skills, adding an extra step here or there, writing a little more neatly, writing larger. That was something that helped me personally a long time ago. I discovered that one of my problems was that I couldn't read my own writing because I was writing so rapidly, and then some numbers looked like other numbers and that kind of thing, and I made mistakes as a result. So, at any rate, we write the factored form in the denominators, and now we identify a common denominator. The common denominator needs to involve every different factor that we see. All right, we see x minus 1. I'll write the common denominator out here. We see x minus 1, so x minus 1 needs to appear in the common denominator. We see x. X needs to appear in the common denominator. We see x plus 1. X plus 1 needs to appear in the common denominator. We see x minus 1. Oh, it's already there. Okay, we don't need to put it in again. That's important to realize here. All right, in this, for this fraction, the missing factors, and we just compare the factors in this denominator with the factors that need to appear in the common denominator to tell which ones to multiply in. Well, clearly, the x and the x plus 1 are missing factors here to cause that common denominator situation, so we'll multiply in the denominator by x times x plus 1. Now, in doing so, we'll need to also multiply those factors into the numerator. The reasoning there is because we're multiplying by a form of 1. All right, 3 times x is 3x, and then 3x times x plus 1 is 3x squared plus 3x. For this one in the middle, we're missing the x plus 1, x minus 1 factors. So we'll need to inject those in here. Now, to show that, I'm going to squeeze some things in here. I'm going to put a plus sign here. The 2 over x I'm going to write just a little bit smaller so we can see that we're multiplying by x plus 1 times x minus 1 in both numerator and denominator. Now, in the numerator, 2 times x plus 1 times x minus 1. Let's see, this product is x squared minus 1. 2 times x squared minus 1, 2x squared minus 2. For this fraction, we're missing the x factor, so we'll multiply here by x over x. In the numerator, it's x times x plus 3, or x squared plus 3x. For the denominator, it's the common denominator as expected. Well, now we have 3 separate fractions all having this common denominator. My suggestion is that we write a distinct step showing this condition before we begin to collect numerators. There's a tendency to try to skip steps right through here, and it's rather important not to. If you're wondering whether a step can or cannot be skipped in algebra, often a key is to say, well, if you have to pause to think about skipping the step, then don't skip it. You should always be writing. All right, let's see. We have the common denominator situation. We take this numerator. We're going to subtract that one. Now, very important to think of this with parenthesis so that we'll change both signs. The 2x squared becomes minus 2x squared. The minus 2 becomes plus 2. All right, then plus, and here, of course, these are just brought down. Now we're looking to collect like terms. 3x squared here, minus 2x squared here would be x squared, and we have another x squared, so that's 2x squared. So we're collecting these 3 terms to get 2x squared. And then the 3x with another 3x out here gives us 6x, and we bring down the plus 2. Now this numerator can be factored. We can take out the common factor 2 if we wish to do so, but it would not lead to a cancellation here, so I'm simply going to leave it in this form. Look at this situation. We can take out the we multiply by